chapter, we're going to be looking at refrigerators. A refrigerator is a device that transfers heat from a low temperature region to a high temperature region. And the objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. In a refrigeration cycle, the working fluid used is refrigerant. And a heat pump. A heat pump is the same thing as a refrigerator with the exception that the objective of the heat pump is to maintain a heated space at high temperature by using the heat out. So if you look at this whole cycle, we have that a refrigerator, this is, again, these diagrams would be from chapter 6. If you think of a refrigerator as a reversed heat engine, it takes work in to move heat from a cold region to a warm region, right? So this would be, for example, the inside of the refrigerator where the desired output of the refrigeration cycle is the Q removed from the cold space. And then a heat pump is the same thing. It operates on the same cycle. It takes work in, moves heat from a cold space to a hot space. But in this case, for example, if the heat pump is trying to heat the house, the desired output would be the heat being rejected from the cycle to the hot space, whereas the desired output of the refrigerator is going to be the heat removed from the cold space that goes into the cycle. If you want to recall, refrigerator, the performance of a refrigerator is not measured by an efficiency. It's actually measured by something called a coefficient of performance. And the definition of the coefficient of performance is the desired output over the required input. Now, the reason why it's called a coefficient of performance is because this value tends to be at times greater than 1, so it is not a percentage, it is a coefficient. So if you wanted to look at a refrigerator, the desired output of the refrigerator is the heat being removed from the cold space, not the heat being rejected from the cycle, but the heat being removed from the cold space going into the cycle, QL. That would be the desired output of a refrigerator, divided by the work required, which is the work into the refrigerator. And the coefficient of performance of a heat pump would be the Q being rejected from the cycle to the space that you're trying to heat, which in this case is a house. So it would be the QH over the work in. And a lot of the times, refrigerators, what they call people tend to talk about what's called the refrigeration load, right? Or basically the tons of refrigeration. A ton of refrigeration is not how much a refrigeration system weighs. A ton of refrigeration is heat rate. It's the equivalent of 212 or 211 kilojoules per minute or 200 BTU per minute. So if I say that my refrigeration has my refrigeration load is 10 tons, it means that the QL coming out of that's being removed from the cold space is 2,110 kilojoules per minute. So it would be 10 tons of refrigeration, or the heat rate would be 10 times 211 kilojoules per minute. Now, let's look first at something called the reverse Carnot cycle, right? The Carnot cycle itself consists of 4 totally reversible processes, 2 isothermal and 2 isentropic. The Carnot cycle has the maximum thermal efficiency for a given maximum and minimum cycle temperature. It serves as a standard against which actual cycles can be compared. All 4 processes that compromise the Carnot cycle can be reversed. Reversing the direction of the processes also reverses the direction of any heat and work interactions. The result is called the reversed Carnot cycle, a cycle that operates in the counterclockwise direction on a TS diagram. Carnot refrigerator or a Carnot heat pump. A refrigerator or heat pump that operates on a reversed Carnot cycle would be called a Carnot refrigerator or a Carnot heat pump. the most efficient refrigeration cycle operating between two specific levels, or between two specific temperature levels, would be that Carnot cycle, that Carnot reverse Carnot cycle. Consider the reverse Carnot cycle executed within the saturation dome of a refrigerant. Right, so here you would have the Carnot cycle would be going to the right, where this would be Q in. But for the reverse Carnot cycle, it goes in the opposite direction, and this becomes Q out. In the Carnot engine, this would go in this direction and be Q out. But in the reverse Carnot engine, or reverse Carnot cycle, this is going in the opposite direction, and this is Q in. Now, as it's also important to mention that for the reverse Carnot engine, you have here the turbine, which is normally here, is replaced with a compressor, and the pump that's normally here is replaced with a turbine. So all the processes are the opposite of what it was for the Carnot heat engine. And just like the Carnot cycle, the Carnot efficiency of a heat engine can be expressed in terms of temperature, the coefficient of performance of a Carnot refrigerator and a Carnot heat pump can also be expressed as a function of the temperatures, right? So a Carnot refrigerator would be 1 over the quantity TH over TL minus 1. And the heat pump would be 1 over the quantity 1 minus TL over TH. Now, in practice, the reverse Carnot cycle is not a suitable model for refrigeration cycles. Processes 2 to 3 and 4 to 1, the isentropic processes, cannot be approximated closely in practice. Process 2 to 3 involves the compression of a liquid vapor mixture, which is not very possible. And process 4 to 1 involves the expansion of a high moisture content refrigerant through a turbine, both of which not practical. So many of the impracticalities associated with the reverse Carnot cycle can be eliminated by vaporizing the refrigerant completely before it is compressed before it's compressed, and by replacing the turbine with a throttling device such as an expansion valve. The cycle that results is called the ideal vapor compression refrigeration cycle. And that is what I'm going to explain in this slide. So we have here what used to be the turbine is now replaced with a compressor. What used to be the boiler is now replaced with a condenser. What used to be the pump is replaced with an expansion valve. And what used to be the condenser is replaced with an evaporator. So what you have in this cycle are 4 processes. You have state 1 starting as a saturated vapor being isotropically compressed to state 2. State 2 to state 3 would be constant pressure heat rejection. State 3 to state 4 would be a throttling expansion, throttling the pressure from the high pressure to the low pressure. And state 4 to state 1 would be constant pressure heat absorption. Now, I want to explain a little bit about this and a little bit about why refrigerant is the working fluid of a refrigeration cycle. Refrigerants are working fluids that have low saturation properties, right? Phase change occurs at low temperatures. So let's say I'm going to try to draw a diagram here. I have a room, right? And we're going to use a window air conditioning unit. So if you go buy a window air conditioning unit, you put it in, this is the outside, and this is the inside. Right, so I want to go ahead and do my best to correlate what's going on with the cycle while explaining how you would correlate that with a with a window air conditioning unit. Now the refrigerant, starting at state 1, is going to be a saturated gas. So it goes into state 1, and what's happening is that now it's compressed to a high pressure state 2. So that happens where the refrigerant is now out here, and this is where QH happens, right? This is where Q is rejected to the outside. What's happening now is that the refrigerant is heated up to, it's a gas, and it's so hot that it rejects heat to the outside air. So basically, the temperature of the refrigerant in this case is higher than the outside air so that it can reject heat to the outside, right? And the operating pressure of the condenser has a saturation pressure that results in a saturation temperature that's greater than the outside air. So what's happening is that now the refrigerant that's a superheated steam is going through these condensation coils. There's a fan taking in air from the outside, and the air is blowing over the coils so that the outside air is absorbing the heat from the refrigerant and causing the refrigerant to condense down to state 3, which is a saturated liquid. Now again, the operating pressure of the condenser has to be high enough so that the saturation temperature of the refrigerant is hotter than the outside air, allowing it to reject air to the outside. Now it comes out of the condensing coil as a saturated liquid, and then goes into a throttling valve. The throttling valve drops the pressure. It drops the pressure significantly, and the temperature also goes down. The temperature goes down. The pressure goes down until it hits the operating pressure of the evaporator. So it comes out of the expansion valve as a saturated mixture. So now I have refrigerant that's going through these evaporator coils. There's a fan taking in inside air, blowing it over the evaporator coils. And what's happening is that the refrigerant is absorbing heat from the air. It's absorbing energy by heat from the air, causing the air temperature to decrease and causing the refrigerant to phase change. So this is an isothermal heat addition because what's the heat being absorbed from the inside air is causing the refrigerant to evaporate, but that evaporation occurs at constant temperature until all of it evaporates. So when it comes out of the evaporating coils, it's again a saturated vapor. And then again, the compressor pushes the pressure up in order to be able to reject the heat to the outside, right? As you compress it, the temperature also goes up, and then it goes through the condensing coils on the outside again, and the cycle starts all over. So what's great is that the refrigerant has saturation properties so that I can reject heat to the outside and absorb heat from the inside. So in a household refrigerator, the tubes in the freezer compartment is where the heat is absorbed, right? That's the cold space. That's where I'm blowing air over the coils inside the refrigerator in order for the refrigerant to cool the inside of the refrigerator, take heat away from inside the refrigerator to keep the inside refrigerator cold. And then the coils behind the refrigerator is heat is dissipated to the kitchen air, right? So then what happens, you go into the compressor, right? There's the saturated vapor from the refrigerant absorbing the heat from the inside of the refrigerator, goes into the compressor, comes out of the compressor as high temperature, high pressure steam, refrigerant steam, and it goes through these condenser coils where it's rejecting Q to the kitchen air, so that now the refrigerant goes from a superheated vapor and gets condensed back down to a saturated liquid, ready to go back through the expansion valve in order to go back into the evaporator coils. Process diagrams. So recall that the area under the process curve in the TS diagram represents the heat transfer for internally reversible processes. So therefore, the area under the process curve for 1 represents the heat absorbed by the refrigerator in the evaporator. And the area under process curve 2-3 represents the heat rejected in the condenser. And another diagram pretty frequently used in analysis is pH diagrams, but we're not going to deal with that very much. Now, in terms of a thermodynamic analysis, all four components associated with the ideal vapor compression refrigeration cycle are steady flow devices. So the kinetic and potential energy changes of the refrigerant are usually small relative to the work and heat transfer terms and are therefore usually neglected. So the steady flow energy balance per unit mass can be reduced to the following, where basically any energy exchange, whether Q in, Q out, or work in, or workout, if there was workout, would be equated to the change in enthalpy. And again, the condenser and the evaporator do not involve work, and the compressor can be approximated as adiabatic and isentropic. So if we were going to go and try to find the coefficient of performance again, right, the coefficient of performance would be the heat absorbed from the cold space for a refrigerator. It would be the heat absorbed from the cold space divided by the work in. The heat absorbed from the cold space is process 1 to 4. So that would be H1 minus H4. And the work in would be process 1 to 2. So that would be H2 minus H1. And likewise, for the coefficient of performance for a heat pump, that would be the Q rejected from the cycle, QH, divided by work in. So that would be equated as H2 minus H3 for QH, and work in again would be H2 minus H1. And if you were to do an energy balance on the entire cycle, you get that the work in is equal to QH minus QL. Now, let's look real quick at the actual vapor compression refrigeration cycle. So the actual vapor compression refrigeration cycles differ from the ideal ones in several ways. One, so basically there are two common reversibilities that you'll see. One is fluid friction, and two is heat transfer to or from the surroundings. So the TS diagram of an actual vapor compression refrigeration cycle is shown below, where you can see that, for example, you can see pressure drop across the evaporator and the condenser, and you can see the effects of fluid friction on this diagram. But in practice, the refrigerant is usually superheated before entering the compressor, so it doesn't necessarily go in as a saturated vapor. It goes in more as a superheated vapor. And then the actual compression process involves frictional effects, which increase the entropy as well as the heat transfer, and may increase or decrease the entropy depending on the direction of the heat transfer. And then the entropy of the refrigerant may increase as well, where process 1 to 2, or decrease for process 1 to 2 prime during an actual compression process. In actual cycles, it is unavoidable to have some pressure drop in the condenser as well as in the lines connecting the condenser to the compressor and to the throttling valve. So the refrigerant is subcooled somewhat as it enters the throttling valve.